All right, let's get started. We left off talking about Chapter 10, gases. Our calculators are back out. We looked into the combined gas law relating pressure, volume, temperature changes for a sample when we put that sample in different conditions. We looked at the ideal gas law, so connecting the idea of moles of gas. If we know how many actual particles are in our gas sample, we can relate that to its volume, pressure, and temperature, again, in our ideal gas law, or PIV-NERT. I tend to use PIV-NERT as a verb sometimes, like if we know the mole amount, pressure, and all those things, I just say, oh, just PIV-NERT, do PIV-NERT, meaning just plug in those values given our gas law constant. And so we'll put these ideas together into the next section here, where we're going to talk about mixtures of gases. We can have pure samples of gases and inspect those, but most of the time we're working with mixtures of gases. So the neat thing about mixtures of gases is that we can do PIV-NERT on the individual parts of a mixture of a gas sample, or we can do PIV-NERT for the entire gas sample. It all depends on how many particles are actually there. So in mixtures, for example, like the air that we breathe, almost 80% of the oxygen, or the air that we breathe, is nitrogen. That should say N2, that's a mistake. N2 gas, about 20% of it is actually oxygen gas. And then there's small parts of other types of gases, argon, CO2, etc. So in the air that we breathe, nitrogen exerts the highest partial pressure of the gas that makes up our atmosphere, because it's present in the largest quantity. And so what we see is this relationship between, okay, how many particles of, or what percentage of the particles are each different component of a mixture, and that relates to the partial pressure of each of those components. And so that brings us to Dalton's law of partial pressure. And this is specific for mixtures, where the total pressure of a mixture is equal to all of the partial pressures of each of those components. So for example, if we had a gas sample that had components A, B, and C in it, we could measure the partial pressures of each of those different components, add them up to be equal to the total pressure that we would actually measure for that entire container. And so the neat thing about partial pressures and all of these things is that pressure, this is the same pressure that we calculated using PIV-NERT, PV equals nRT. We can actually PIV-NERT each and every one of these components, but in order to calculate the partial pressure of component C, right, we would have to use the number of moles of component C that we actually have. Right? If we wanted to calculate the partial pressure of B, we would want to use the mole amount of B atoms that we have. If we wanted to calculate the partial pressure of A, we would want to use the mole amount of A particles that we have. So we can PIV-NERT each and every one of those components. But if we wanted to PIV-NERT calculate the total pressure of our system, we would actually want to use the total number of moles in our actual system, where N total in this example would be equal to the sum of the A particles plus the sum of the B particles plus the sum of the C particles, right? So we can PIV-NERT each of the components, and we can add up those components to get up our total pressure of our system. All right. So another way that we can talk about gases and partial pressures is terms of mole fraction, because the pressure of a gas sample is just dependent on how many gas particles are present. And so if we're working with a mixture, sometimes it's useful for us to talk about, okay, what fraction of the particles are this component, what fraction is this component. And so that's what mole fraction is, where we can relate each of the components based upon its particles. So the symbol for mole fraction is chi. It's like a fancy looking X. And so what this equation is just saying is that the mole fraction of a component is equal to how many moles of that component am I working with over the total number of particles that are present. right? So if I have a container with like 100 particles in it, 100 gas particles, but let's say 20 of those particles were like oxygen molecules. The mole fraction of oxygen would be 20 over 100. It would be, 20% or 0.20 would be the mole fraction of oxygen. And so mole fractions will always add up to 1 if you consider all of the different components. So it's essentially like we're just looking at the fraction of each of those components in a fractional way. And so mole fraction will also allow us to relate our partial pressure. This is our partial pressure of that component, all right, to the total pressure of the system. If we know, like, let's say 50% of our particles are component A, if you multiply the total pressure by that mole fraction, you'll get the partial pressure of that component. And so really this is just a consequence of utilizing our Pivnert equation and understanding that the amount of moles of gas that I have present relate to the pressure that's actually present. All right, so that's the concept. So let's actually do some math, right? Using all of these different terms. We have mole fraction, chi, we have partial pressure there, and then of course we will probably be using Pivnert. All right, so we have a mixture, 10 grams of helium and 10 grams of neon, and we put it into, or we charge it into a 20-liter tank at 298 Kelvin. Charge is just like a fancy word for fill, specific to gases. All right, so when you fill a gas container, sometimes you say you charge it with that gas. So I got a couple questions here. We have a mixture, it's helium and neon, but I give you masses. So let's figure out what is the total pressure of this tank, what are the partial pressures of each of the components, and then finally what are the mole fractions of each of these components. So let's look at this mathematically. I have the molar masses of helium and neon here, and hopefully you recognize, oh, the first thing I need to do is convert those gram amounts to mole amounts so I can use Pivnert and mole fraction, and et cetera. So that should be review in a bit. So moles of helium, we have 10 grams of helium. The molar mass of helium is basically 4. 4 grams is 1 mole of helium. Right, and that'll give me a mole amount of helium. Then I want to do the same thing to neon. So there is 10 grams of neon as well, but we want to use the molar mass of neon, so like 20.18 grams is 1 mole. All right, so we have equal masses of each of these components, neon and helium, but what we'll see here is that there is 2.50 moles of helium present, and about half a mole, so 0.495 moles of neon present, all right, in our sample. So we have like 2.5 moles of helium, half a mole of neon. Which particle is exerting more of the pressure of the total sample? Both of those things are present in this container. So which one is contributing the most to the pressure of this system? Helium, yeah, because there's just more particles present. And so there's a couple ways that we can kind of approach this next question. So in our container, we have both of these things present. We have moles of helium, moles of neon. So what might be useful for us is to calculate, okay, well, how many moles of gas is present total? It's about 3. Yeah, let's just round up to 3. So there's 3 moles of gas present total, all right? Where 2.5 are helium and half a mole is neon. So if I go ahead and Pivnert N total, and I use 3 moles in place of the N in Pivnert, what would I be calculating? What pressure would I calculate if I use N total here? I would calculate pressure. Would I be calculating a partial pressure? No, I would be calculating the total pressure of the entire system. All right, and that's how we get that first component, that first question here. So if I go ahead and use this N total, and I'm actually calculating P total in this case. So P total is what I'm calculating, and then I'll Pivnert this. So 20 liters equals N, so 3 moles times R times temperature, so times 298. And so if you calculate that, I have that there, all right, calculate that. You get that if you put 3 moles of gas into this 20-liter container, at 298 Kelvin, you'll get like 3.66 ATM for the total pressure of this container. All right. Okay. So that's the total pressure of the container. Now the next question is, what are the partial pressures exerted by helium and neon individually? And so here, if we want partial pressures, if we use the actual mole amount of each of the components present, so essentially if we PIV-NERT these mole amounts that we already calculated, that's how we're going to get the partial pressure of each of those components. So if we PIV-NERT using 2.5 moles of helium and of 0.495 moles of neon, we should get different pressure values. So those pressure values, if you calculate them, is something like, so it's in the corner. So helium is exerting 3.06 atmospheres of pressure, and then neon is 0.606 ATM of pressure. So using those respective N mole values for each of the components, you'll get the partial pressures of each of those components. So what's special about those two pressures that I just calculated? What's special about those? What's special? If you add them up, it's what? 3.66, right? If you add up those two values, we should get our total pressure, because these are our partial pressures. This is the partial pressure of helium. Here is our partial pressure of neon. If you add those two numbers up, you should get the total pressure of the entire system. Great. So those two partial pressures add up to the total pressure that we just got. All right. So now we can calculate the mole fractions of helium and neon. And so we kind of already predicted that helium is going to contribute more to the partial pressure. And the reason is because there's more moles of helium present. So the last question here, we can calculate the mole fraction of helium a couple ways. We can take the mole amount of helium we have, so 2.50 moles of helium, and we want to divide by the total number of moles of gas that we have present. So basically 3.0 moles of gas. And that will give me the mole fraction of helium, right? And then we can also calculate the mole fraction of neon. It's just going to be whatever's left over, but in this case it's 0.50, or I guess 495, whatever, over 3 will give us another number. So let's see, those numbers are 0.835. So 83 or 84% of this sample is helium, and then the rest, like 16%, is neon there, right? So to calculate mole fraction, we can use mole amounts to calculate the different fraction of those components, but what we can also do, and this is going to be useful in 1220, is that we can use the mole amounts, the mole amount of neon and the total mole amount to calculate mole fraction, but what we can also do is take the partial pressure of neon over the total pressure of the system, and we will get the same exact number. So if I look at these values here, here's the partial pressure of neon. Here's the total pressure of the system. You can check for yourself if you put these two numbers together, 0.606 ATM over 3.66, you will still get 0.165, right? So the ratio of the pressures and the ratio of the mole amounts will both get you mole fraction. And that's, again, just a consequence of how our ideal gas law equation works. And then finally, what is special about these two numbers, 0.835 and 0.165? What's special about those two numbers? Add them up, they add up to 1, because there's only two components present, all right? So the fractional amounts of each of them have to add up to 1. If there were 3 components, all three mole fractions add up to 1 there. All right, so that's a mathematical way to inspect partial pressures, mole fraction, all right? This slide would never be on the exam. Only like one part of this question would ever be on the exam. So let's look at some conceptual questions. Some conceptual questions instead that may or may not show up on your exam. Okay, so here I have a picture where I have some blue particles and black particles. Where should I put these? Right there. All right, so those are gas particles. So based upon this picture, which gas is present in the larger amount, has the larger mole fraction? Which one? Just based upon the picture, black or blue? Yeah, it looks like black is bigger. Why don't we just go ahead and calculate the mole fraction of each of them? How many blue gas particles are there? 4, and then how many black? 6. Okay, so that means the total number of particles I have is 10. So based upon these numbers, what is the mole fraction of the black particles? 6 over 10, so 0.6. So 60% of the sample is black particles. And then that means that 4 over 10, or 40%, of this sample are the blue particles. Great. Great. All right, so then which gas exerts more pressure? The black sample or the blue sample? Based upon this. Black, yes, because it's present in the larger amount. All right. All right, so that's just a conceptual question. So let's add a tiny bit of math to it. So we're still working with the same picture. So if the total pressure of this container is 2 atmospheres, so that's total, what are the partial pressures of each of them? Right? So all 10 gas particles add up or contribute 2 atmospheres of pressure. So then how can we calculate the partial pressure of the blue particles? We want to take the mole fraction of the blue particles and then multiply it by the total pressure. So what I'm going to do is take the mole fraction of blue, multiply by the total, right? So essentially 40% of that 2 atmospheres, which is the total, is going to be what blue contributes. So blue is contributing 0.8 atmospheres, right, of pressure. Then we do the same thing for black, but you can kind of just, you know, tell how much partial pressure is left, right? Because both of them have to add up to 2. So that missing piece has to contribute 1.2 atmospheres. But we can calculate it as well, because it's the same idea that the partial pressure of the black particles times the total pressure has to equal the partial pressure of black. So it would be 0.6 in this case times the total 2 atmospheres equals 1.2 atmospheres. So those are the partial pressures of both of the components. They add up to the total pressure here. And so the relationship is via the mole fractions that we initially calculated. All right, so here is a slightly trickier one. So here I'm telling you that the partial pressure of the blue sample is 1.2 atmospheres. What is the total pressure of the container? Right? So this one's a little bit trickier. I know that the total pressure of the container is equal to the partial pressures of the blue particles plus the partial pressures of the black particles. So I know one of them. I know one of those values. I just need to figure out, okay, if the partial pressure of the blue particles is 1.2, what is the partial pressure of the black particles? There's a couple ways we can do this. All right, if the blue is contributing 1.2 atmospheres, we know that the blue particles are 0.4, so 40% of our sample. Shouldn't we be able to scale that pressure up? Because I know that the black particles contribute 60% of the sample. So there's a couple ways you can do this. You can say, oh, 40% of the sample, I can say 40% of the sample is the blue particles and 60% of the sample is the black particles. And so scaling this up, I should be able to get the partial pressure of the black particles, which I think is something like 1.8 atmospheres. There's actually another way we can do it. If we start with 1.2 atmospheres of the blue particles, we can also do this another way. How many blue particles are in the container? 4. And then how many black particles are in the container? 6. So for every 4 blue particles, there are 6 black particles. And so that also scales up our partial pressures in this example. all right? And so you get that the black sample is then, you get the same exact answer, 1.8 atmospheres, all right? So that's the partial pressure of the black particles, but if you look at the corner, that's not the answer that I want. What's the actual answer that I want in this question? The total pressure. So the answer is not 1.8, it's actually 1.8 plus the original 1.2 that's there, all right? So in order to get 3 atmospheres, we do 1.2 plus 1.8, that's how we get 3.0. And you can check for yourself. If the total pressure of the system is 3 atmospheres and you do the 40 and 60%, all right, for the mole fractions, you'll get those same partial pressures we just calculated. And that's a way to check yourself. All right, so that one's a little bit more conceptual plus a little bit of math at the end. All right, so partial pressures, we can Pivnert the components. We can Pivnert the total amount of gas that's present. They always add up to the total pressure. The mole fractions always add up to 1. All right, and so that's just a consequence of mixtures. It doesn't matter what the gas is inside the container, it's just how many particles are present is what contributes to volume, what contributes to pressure. All right, so that's basically most of the math in this chapter. So we're gonna look at some ideas of why the ideal gas law works. So PV equals nRT, right? PV equals nRT, right? That's the ideal gas law. So laws, any type of law is, you know, an equation or a statement that describes a observation, some type of phenomena, like the law of gravity. We know that if we drop an apple 1,000,000 times, it will always fall. Laws explain phenomena, observations that we see. Theories explain why things work the way they do. So the ideal gas law explains how pressure, volume, temperature, and moles, how they're all related. And it always works for the most part, right? The kinetic molecular theory describes why this equation works, all right? So we looked at the equation, we did the math, now let's look into why this equation works and maybe sometimes why it doesn't, sometimes it doesn't work, right? So that's kinetic molecular theory. It explains all of our gas laws that we talked about previously. And so really what this, these different postulates or assumptions it describes what we think gases behave like. And so the first postulate here is, okay, gases are particles, and they're in constant random motion traveling in straight lines. So we think about like a gas sample, there's particles on the inside, they're all moving around like crazy in straight lines, bouncing off the walls of the container, stuff like that. All right, so that's the first postulate. It describes how gases behave. The second postulate, and we kind of already talked about this before, in a gas sample, do the actual particles take up a lot of space? No. We talked about like gas samples, like if we have a balloon filled with helium, that balloon is mostly empty space. There are particles in there bouncing around to give that pressure and to give that volume, but a gas sample is mostly empty space. Unlike a liquid sample. In a liquid sample, those liquid particles, they're all condensed together, but in a gas, all of the particles are very, very spread out. All right, so that's kind of the second postulate. Space occupied by gas particles is very, very small compared to the container itself. So I can, draw a picture, a balloon with a gas inside. Those gas particles only take up a tiny, tiny bit of space because they're always bouncing around. It's mostly empty space, so we can basically ignore the volume of the particles themselves, that the space they occupy is just the container that it's in. So that's the second postulate. All right, the third postulate is that particles are not attracted to one another, meaning that you can think of gas particles as like a physics problem where two balls are just colliding with one another. All right, all of their energy is transferred. This is also kind of the fourth postulate as well. When the particles bounce off one another, there's no attractive forces there. It's just a purely elastic collision where all of that energy is transferred from one to another. Both particles come in with a certain kinetic energy, they leave with that same amount of kinetic energy. There's no loss of energy. This is all elastic collisions, not inelastic. So those are the third and fourth postulates. Particles aren't attracted to one another. And then the fifth postulate, and this is important, where pressure comes from. Pressure of your sample, if you think about a balloon. The reason a balloon exerts pressure is because the particles that are all moving in straight lines inside the container, they're bouncing off the walls of the container. So the idea here is that collisions, all right, is the amount of collisions is proportional to the pressure of your sample. So the more your particles are colliding with the walls of the container, the higher the pressure. If your particles aren't colliding with the walls of the container, then you're going to see a lower pressure, right? So it's collisions that produce pressure for our gas sample. And what's the last thing here? Oh, and then finally, related to that, kinetic energy of our sample is proportional to the temperature of our sample. So we already know that about samples, that temperature is the measure of average kinetic energy, and we see that with gases as well. As we heat up a sample, we increase the total amount of kinetic energy in that sample because particles are moving faster. Hot things move faster than cold things, right? And this relates to collisions. The whole idea that collisions relate to pressure, we'll see that phenomena come up in some of the observations we see. All right. Okay, great. All right, so let's talk about gas speeds. All right, so we know temperature is the measure of average kinetic energy of our sample. So let's think about how that relates to gas samples specifically. So we have a balloon full of a gas. We have a bunch of particles. They're all bouncing and moving around that space in the balloon. Do you think all of the gas particles are moving at the same exact speed? No. We have a distribution of speeds because all particles are unique. All right, they're all bouncing differently. They're gaining or losing like kinetic energy as they're bouncing, but we maintain this average kinetic energy based upon the temperature of the sample. So all these particles are unique, and so at a certain temperature, if we actually went ahead and measured, clocked every velocity of every single particle in that container, we would see a distribution of molecular speeds, kind of like grade distributions, right? All students are unique, but we all get different grades. And so that's kind of what we see here, where we have this most probable speed for this sample. So let's just look at one of these graphs, right? So this is a gas sample at 100 Kelvin, right? So pretty cold. Most of the particles are moving at this speed, but you see that some particles are moving a little bit slower, some are moving a lot faster. And so we call this a Maxwell-Boltzmann distribution because it follows a different type of mathematics here. It's not like a Gaussian distribution, it's not like a bell curve. What we see here is that this curve has a long tail on the high side. And so we call this a Maxwell-Boltzmann distribution, that we can't have a particle traveling at below 0 meters per second, but we can have particles moving faster. So it's kind of like an unequal bell curve, right? That's a Maxwell-Boltzmann distribution. So let's look at these graphs. So this graph is showing the different speeds that molecules will have in a sample that's at 100 degrees Celsius, or sorry, 100 Kelvin. What happens when we increase the temperature to 200 Kelvin? What happens to our graph? It shifts, but shifts how? It shifts to higher, faster velocities. If we increase the temperature even more, we can see, oh yeah, that most probable speed, these graphs are getting faster and they're kind of flattening out, right? So at higher temperatures like 500 Kelvin, we see a larger distribution of molecular speeds, but we see that it's shifting to higher and higher velocities on average. And so that's consistent with the idea that, oh, hotter molecules move faster. And we see that with the distribution. The distribution is pushing itself towards higher speeds. But we still have, somewhat slow moving particles. It's just the average is changing there, right? Okay, so we talked about, these most probable speeds moving to higher velocities, but the problem is that determining what the most probable speed of a gas sample is kind of difficult, right? To get a most probable speed, we would actually have to measure the speed of all of the particles, make a histogram, and figure out where the peak is. That's kind of difficult to do. So scientists, we want a way to take a measurement from the lab and relate it to a number that's useful to us. And so that is where we use root mean squared velocity. And so that's this equation right here. All right, so this equation right here, root mean squared velocity, we take 3 times r. So this r is a different r. This is the 8.314 joule mole Kelvin r. Did we use this one before? This R, maybe? No? Okay, so this is the R gas law constant that has a energy unit within it because we're relating kinetic energy to temperature in this example. And so we want to use that different R. And so what we see is that this root mean squared velocity is related to, 3 and R, which are constants. It's related to the molar mass of your sample, right, mass of your sample, and it's also related to temperature. All right, so the idea here is that we can calculate this velocity with variables or values we can actually look up and actually measure. All right, so this root mean squared velocity, it is not, I'll show you where the root mean squared velocity is. So like right here on this graph, this is your most probable speed. That's hard to measure without a graph. Like I can't just like look at a sample and be like, oh yeah, that's the most probable speed. That's hard to do. Average speed is also kind of hard to measure. So this is where your average will lie, is a little bit above the most probable speed, and it's because of the tail of the Maxwell-Boltzmann distribution, right? And then where your RMS or root mean squared velocity is right here on your graph. So it's a little bit higher up than your average and a little bit higher up than, a little bit faster than your most probable speed. But the great thing is that we can compare RMS speeds of different samples at different temperatures, right? As long as we're always comparing RMS speed to another RMS speed, we can see, oh, this sample is faster than this sample. Based upon comparing root mean squared velocities. And this is more useful to us because we can actually use values that we can measure. Temperature, is that something you can measure? Yeah, you can measure temperature. Can you know the molar mass of your sample? Yeah, you can. So those are things that we can actually compute, and then we get a speed that is useful to us, that we can compare to other samples. So we're going to be using RMS speed. But in order to get RMS speed to come out in the unit of meters per second, we need to, use the equation as a vending machine. We got to be smart about this. R, the gas law constant, is in the unit of a joule. So that means molar mass must be in the unit of kilograms per mole in order to use this correctly because of the unit of what a joule is. Temperature, of course, must be in Kelvin, and then the gas law constant we use is the 8.314 value. And so we can get RMS speed that way. All right, so from this equation, we can actually get a couple trends. So this is our root mean squared speed. So this is how we compare different speeds of gas samples. Think about how this equation changes if we increase the temperature or change the molar mass of our sample. Think about how mathematically the number changes as we change these things. So if we keep temperature constant for a sample, but we increase the molar mass of the gas, how will this speed change? So temperature stays constant, but molar mass increases. How does root mean squared? How does that value change? It gets smaller because molar mass, if we make that number bigger, it's a bigger number in the denominator, so that whole number for root mean squared velocity gets smaller. So speed will decrease, right, when molar mass increases. And again, to me, that's not a trend to memorize. It literally comes from the equation of root mean squared speed, right? Okay, so let's say we have the same sample, so molar mass stays constant. How does root mean squared velocity change as we increase the temperature of our sample? So let's look at this equation again. This time we're changing the numerator. We're making temperature bigger. How does root mean squared change? Increases. Yeah, speed will increase. But does that make sense intuitively? Hotter samples move faster. And the root mean squared velocity equation tells us the same thing. All right, so as temperature increases, speed increases. All right. So if we want to like kind of collectively think about these trends, so root mean squared velocity increases when temperature increases or when molar mass decreases. And we can see that in these graphs here, all right? We already looked at these. Hot molecules move faster. We see that the Boltzmann distribution flattens out, they get faster. If we look at hot molecules, so here, 1000 Kelvin, those particles, the majority of them are moving faster than the cold particles, all right? But we can also change root mean squared velocity using molar mass. If we're looking at different samples with different molar masses, if we look at this graph, which sample is moving on average the fastest? Oxygen or helium or hydrogen? Hydrogen's moving a lot faster, but why? The particles are lighter, and so if all of these samples are at the same temperature, all of them technically have the same kinetic energy, but because the hydrogen molecules are a lot lighter, they're moving a lot faster, right? Because they all have the same kinetic energy. So in this picture, these are all at the same temperature. So hydrogen is the fastest, all right? While oxygen is the slowest, and all we're doing is comparing molar masses of these things. All right, so I guess the generalization is light molecules will move faster, or I guess, you know, not as heavy molecules are moving faster while heavy molecules move slower at the same temperature, right? Okay. Okay, so, all right, so there we go. So let's put these, oh, nope, let's do an example. Okay. Exam questions that require no math. All right, so I had the root mean squared equation up there for you, but we're not going to calculate anything. We're just going to use the equation as a way to get our trends. All right, so I have two curves here. So make sure you recognize, oh, I'm looking at a Boltzmann distribution of molecular speeds of something A and something B. Okay, if the curves A and B refer to two different gas samples, hydrogen and oxygen at the same temperature, which one is which? So, which sample is moving faster, A or B? B is going faster. So which one of these samples will move faster, hydrogen gas or oxygen gas? Hydrogen, because it's lighter, yes. And so that means A is going to be oxygen because it's heavier. So the idea here, they're both at the same temperature, so they both have the same kinetic energy. So if we think about kinetic energy, 1/2 mv squared, if both of them have the same kinetic energy, their masses are different. So hydrogen, since it's lighter, will have a larger velocity, or like faster velocity there. All right, so hydrogen's the lighter one. Okay, so same graph. If A and B refer to gases at the same gas at two different temperatures, which is the gas at the higher temperature, A or B? B, yes, B, because it's moving faster. And so again, if we look at our root mean squared equation, we see that molecular speeds will increase if temperature increases, but molar mass decreases. Light molecules, light and hot molecules will move the fastest there. All right, so that requires no math. Okay, so let's talk about some other properties relating to kinetic molecular theory. All right, so gases are constantly moving. All right, but you know what's interesting here? Let me go back to the slide up here. All right, so let's look at this example. Okay, so oxygen molecules, they're moving really fast. They're moving like, I don't know, 300 meters per second, right? That's what this graph is trying to say, that most oxygen particles are moving 300 meters per second. That's really, really fast, okay? So that's interesting because, you know, I can't notice gas particles moving that fast. Like, let's say I break a bottle of perfume in the corner of the room, right? That perfume has like gas particles in it that we can smell. Will you smell those particles instantly the moment I break it in the corner of the room? Like, especially the people up there? No, it takes time for gas particles to move across a room. All right, but isn't it weird? Gas particles, but they're moving at like 300, 500 meters per second. And so the reason that gas particles aren't, reaching our nostrils that fast is because gas particles, they're colliding with one another. All right, so in order for a gas particle to make it from the corner of the room up to the balcony, it has to bounce its way all the way up to your nose. It doesn't just make a beeline straight into your nose. So that's what we call a mean-free path for a gas particle. That gas particles, they don't move in straight lines. All right, it takes time to get from this point to this point. All right, and that's compounded by the fact that they are colliding with one another in order to get from one spot to another. All right, and so this is the idea of diffusion. So what I'm demonstrating, if I would, break a bottle of perfume in the corner of the room, is diffusion. It takes time for those gas particles to diffuse its way to the other side of the room, even though gas particles are moving really, really fast. Okay, so let's actually think about diffusion numerically. Well, so here's the thing. Diffusion is related to mean-free path, how a gas particle travels from one spot to another. So that's a little bit difficult for us to quantify. So instead, we're going to actually talk about effusion. So effusion, right here, is similar. It's still gas particles going from one side of a container to another, but it's not, so like in diffusion, we remove the partition between one side of this container to another, and we watch how all of the particles move from one side to another. But effusion is a pinhole, where we have all the gas particles on one side of the container, and we watch and see, okay, how does the gas escape through this pinhole to the other side? So effusion is a lot easier for us to quantify because it happens slower, right? But the idea here is that the rate of effusion is related to how the particles collide with one another, how the particles collide with the walls of the container. A gas particle will go to the other side of the container if it collides with the pinhole, right? That's when a gas particle will switch to the other side. And so what we see here is as collision rates of our sample increases, we'll see our effusion rate also increase. So we already talked about collision rate is related to your root mean square speed of your sample. If your sample is moving faster, then it's colliding with the walls of the container more. If your sample is colliding with the walls of the container more, it's going to effuse faster. Or it's going to move to the other side of the container faster as well. So that's kind of the strategy you want to think about here. Effusion is related to all the things we've talked about already, root mean squared speed, collision rate, it's all related. So let's think about this. Okay, effusion is related to collision rate. Things will effuse faster if it's colliding more. So particle speed will increase, as particle speed increases, so this is RMS speed. As it increases, how does collision rate change? Does it increase or decrease? Increase, yes. Particles are colliding more if they're moving faster. So that means if we change the temperature of our gas sample, how does the collision rate change? It should change how? Heat up our sample? Yes, it should also increase because your particles are moving faster. All right, and so both of these things are increasing collision rate, so therefore effusion rate will also increase. All right, so then which has a higher collision rate? A heavy particle or a light particle at the same temperature? Light particle, yes, because, so a not heavy particle, because I realize light particle also means photon, but that's not what we're talking about here. We're talking about things with small molar masses. Yes, so all of these things mean faster particles, faster collision rates, faster effusion rates. All right, so that's the trend that we see. Effusion rate increases with temperature but decreases with molar mass. This also is just the same thing as RMS speed. Particles moving faster, collide more, effuse faster. All right, so effusion rate. is useful for us to compare a fusion of two different gases. We can use Graham's law to look at this. If you are assigned the makeup lab KMT, this is what KMT is about. Graham's law of fusing different gases. So we can make a comparison of the rate of effusion for two different gas samples based upon their molar masses, assuming that they're effusing at the same temperature. All right, if they're at the same temperature, they have the same kinetic energy. So to compare effusion rates, all we have to do is compare those molar masses, right? So we see that the effusion rate of compound A over B, so that ratio of the effusion rates, equals the square root of the molar masses B over A. So do note how it changes, and the reason is because as molar mass increases, we see effusion rate decrease because particles are moving slower, right? So yeah, rate of effusion is inversely proportional to the square root of the mass of particles. So here, let's think about this. So here we're always talking about rates of effusion, so how fast things effuse. So how is rate of effusion related to time it takes something to empty itself, time to effuse, if we think about that. The faster something goes, the shorter amount of time it should take for that, that container to empty itself, to effuse itself empty. And so that's what we see in this picture. So here I have two balloons, nitrogen and helium. They're both at the same temperature. I'm going to put a pinhole in each of them. Based upon everything we just said, which balloon's going to effuse faster? Nitrogen or helium? And what factor did we look at? Helium's going to effuse faster because it's lighter. Yes, the particles are moving faster. But if I let a set amount of time go by, so helium's effusing faster, what will the after picture look like? Which balloon is going to be smaller? Helium's going to be smaller, yes, because it takes less time for helium to effuse itself dry. So the idea here is that, the time it takes to effuse is inversely proportional to the effusion rate. Helium effuses faster, so that means it takes less time for it to empty itself, all right? Because there's different ways we can ask this question. All right, which balloon has the higher effusion rate? It would be helium, but which balloon takes longer to effuse, meaning in terms of like seconds or time? That would be nitrogen because it has a smaller effusion rate. Okay, all right, as rate increase, time to empty decreases. That's what I should have said. Okay, so let's do a problem here. Okay, we have two identical tanks with equal number of moles of HF gas and HBr gas, and we develop pinhole leaks in them. Yikes. All right, so hopefully you recognize, oh, this is a fusion. Okay. Those are the molar masses. We have HF and HBr. So based upon that information, which gas effuses faster, HF or HBr? HF, because it's lighter. Yes, the particles are moving faster. But then which tank empties first? The faster one or the slower one? The faster one, yes. I changed the wording there. Okay. All right, and then so finally, will the HF tank effuse 2 times faster or 4 times faster than the HBr tank? What do we think? So I'm showing you, let's calculate the ratio of the rates, the effusion rates of HF over HBr. So we're using Graham's law here. So when we compare the rates, we actually want to do what? Compare the molar masses. Yeah, so if we calculate the molar masses, we want to put HBr on top. So that's about 80 grams per mole, divided by about 20 grams per mole. But Graham's law says that this whole thing has to be square rooted, yes. So if we compare the rates, it's square root of 4. So the HF tank actually effuses 2 times as fast, not 4 times as fast, right? Yes, HBr is 4 times heavier than the other molecule, but because we have to square root it, it's only 2 times, it diffuses 2 times as fast, right? And I just did estimations, okay? You can get a better number, but 2 times as fast is good enough. All right, so that's a fusion. That's something we can quantify and relate directly into collision rate, which we directly related into root mean square speed. Everything just comes back to root mean square speed. How does temperature affect the rate or speed of our particles, thus affect collision rate? How does molar mass change those collision rates, molecular speeds as well? Okay, so that's kinetic molecular theory and a fusion. So let's move on to the last part of the chapter, which is where I tell you that everything we learned was kind of a little bit wrong. Yeah, so we learned about the ideal gas law, right? Pivner, easy, plug and chug. But the thing is that not all gas samples follow the ideal gas law. That's why we call it ideal. Only ideal gases, certain kinds of gases, follow PV equals nRT. Sometimes gases don't follow PV equals nRT. Rats. So I'll show you this, this graph again. Remember we calculated how much 1 mole of gas occupies at STP? Remember we calculated that? STP stands for what? Standard temperature and pressure, which means 0 degrees Celsius and 1 atmosphere. So we calculated that 1 mole of gas occupies 22.4 liters. But I showed you this graph of different molar volumes of gases. Do all of them say 22.4? Do most of them do? Most of them do. Most of them say 22.4, but some of them don't. So we see here an ideal gas is 22.4 liters, but chlorine is a little bit less. We see CO2 is also a little bit off. So what we're going to do in this last part of the chapter is explain, well, why are these ones so off? They're not like a lot different, but they're significantly different. They're not that 22.4 that we got before, and so we'll look into the reasons why some of these compounds deviate a little bit from the ideal gas law, while these compounds, helium, hydrogen, nitrogen, they fall pretty close to the ideal gas law, all right? And so we're going to talk about our real gases, so gases that don't fall under the ideal gas law equation, and we're going to use the van der Waals equation to describe real gases. But the thing is, yes, the van der Waals equation looks really scary, but it's not. It's not. The van der Waals equation is just PV equals nRT with some sprinkles on it, all right? So here, this term is your pressure term with an adjustment on it. This parenthesis is your volume term from the ideal gas law with a little sprinkles on it, with a little adjustment. That's it. And then the other side of the equation is the exact same. So that's what the van der Waals equation does. It just adjusts for pressure and it adjusts for volume, because what we'll see here is that the some of the tenets of kinetic molecular theory break down at certain conditions. And we'll see these new terms, A and B, and we'll talk about that in a little bit. Okay, so what are ideal conditions? I like to remember ideal conditions are earthly conditions. On Earth, we have a fairly low pressure, 1 atmosphere. That's really low, 1. That's a small number, right? 1's a small number. Temperature is really high. So room temperature is like 20 degrees Celsius, so almost like 300 Kelvin, all right? That's earthly conditions. That's a really high temperature. So ideal conditions are low pressures, high temperatures. And there's a reason. The tenets of kinetic molecular theory work very, very well at low pressure and high temperature. So that means non-ideal conditions, when we have to consider gases to be real, are not those conditions. So non-ideal conditions are actually high pressure or low temperature. Gases don't behave ideally at those conditions, and I'll show you here. All right, so if we look at this graph, right, if you hear a whole bunch of gases, so right here, this is where I've dotted it blue or green. This is low pressure, and so we see at this pressure, an ideal gas will fall really closely in line with the ideal gas law when we're at very, very low conditions. But when we look at all of these gases, once we start to increase pressure, like increase the pressure to 800 atm, we see that these lines deviate a lot from ideal conditions. So we see at very, very low pressures, we fall right on that ideal line, but anywhere at really, really high pressures, we deviate either below or above it. All right, we start to deviate, all right? So high pressure, we see these lines deviate, okay? Real gases. What's the other condition for non-ideal? Low temperature, all right? And so that's what this graph shows, okay? So remember, this line means an ideal gas, and so here are 3 different samples of gases, but at different temperatures. So it's the same, increasing the pressure thing. So we see at low temperatures, this gas changes away from ideality a lot because it's at low temperature. But if we look at a sample that's really, really hot, like 1000 Kelvin, we see, does that blue line deviate as much as that green line? No. So we see that the really, really hot sample, it deviates a little bit, but not as much as our really cold sample. So here at 1000 Kelvin, there's less deviation. So we can say here that hot samples, all right, fall more in line with ideal conditions. So we're going to see less deviations. Right? And so that kind of explains, non-ideal conditions are either high temperature or or high pressure, low temperature. Low temperature samples will deviate much, much more away from ideality. Okay, and so here are the reasons. It's because tenets of our kinetic molecular theory break down, right? At high pressure, gas particles actually do contribute volume to the container. So one of our postulates breaks down, right, at high pressures. At low temperatures, real gases actually do attract one another, all right, and it starts to matter. And that's why we have to do some, alterations to our PIV-NERT to account for volume of particles and the attractions particles have to one another. All right, okay, so yes. So I mentioned, our van der Waals equation, the real ideal gas law, or the real gas law, has these new terms in it, this A and B term. So A stands for attractions, right? And so that A term, here's a table of a bunch of different A terms for molecules. It just is a number that quantifies how attracted molecules are to one another. Higher number, more attractions particles have to one another. Right? Because remember, tenets of kinetic molecular theory are breaking down now, so we actually have to consider particle attractions. The B term stands for size, right? So larger particles, larger B term. Typically, this is just molar mass, right? So if we look at the molar mass of a compound, the bigger the number, the higher the B term. All right, and so for now, what we're going to say is as B increases, A usually increases. We're going to just say that for now. Because in chapter 11, we'll talk about intermolecular forces. We haven't learned about them yet, but for now, we're just going to say as B increases, A increases. As particles get heavier, the attractions between particles increases as well. So we'll just say that for now, right? Heavy particles have a large B and A term. That's what we're going to say. And that's what we kind of see in this graph. As B increases down this graph, we see most of these numbers increase as well. Okay. Okay, so let's talk about why the B terms and A terms, why they matter at high pressures and low temperatures. So at high pressure, that's one of our non-ideal conditions. The B term dominates. Okay, so pretend we have a container of a gas. Let's say that the volume is rigid, all right, that it's just like a 1 liter container. How do I increase the pressure inside this container without changing the volume? Add gas. If I add a bunch of gas to this container, won't the pressure increase? Yeah. So how do I increase the pressure a lot? Add a bunch of gas. But if I increase the pressure of the container so much, don't I have to add a bunch of particles, like a ton of particles, to a point where you're trying to shove a bunch of particles into a small space? So this is why at high pressures, the size of the particles start to matter, because you're trying to shove a bunch of particles into a small space, all right? Once the pressure is really high. When the pressure is really, really low, there's a ton of space between particles. Low pressure, you don't need a lot of gas particles to do that. So the size doesn't matter, but it's at high pressures their size actually matters, because there's less space between the particles themselves. All right, so here, yes, at high pressure, B term dominates. Molecules are no longer separated by distances. So that's why this B term is attached to the volume term in the Pivnert equation. So you can think about it like this. You know, at low pressure, there's lots of space between particles, but at really, really high pressures, the actual size of the particles start to matter. And it contributes to the free space, or it takes away from the free space particles are allowed to move. Right, so that's why we have this adjustment term that we put into the van der Waals equation. All right, high pressure, B term dominates. Size of particles matter at high pressures. All right, so the other non-ideal condition was low temperatures. So let me ask you, at low temperatures, particles are moving how? Slow or fast? Slow, very slow. All right, so when particles are moving slow, remember, so we're thinking about real gases, so we're no longer thinking collisions are completely elastic. What does elastic mean in physics? Hopefully you took physics, right? I don't know. It means that when they collide, there's a complete transfer of energy, yes. But now we're talking about inelastic conditions. So when two particles are moving fairly slowly, they're slightly attracted to one another, they're sticky. All right, so when they collide, they're going to actually stick to one another a little bit before they go off and bounce off one another. They lose a little bit of energy, right? So at low temperatures, this is really, really important, because at low temperatures, particles already have low kinetic energy. So if there's a little bit of stickiness, all right, a little bit of stickiness, there's a little bit of kinetic energy loss, it matters more when the particles are moving slower, like at low temperatures. And that's what we say here. Right, here's another way to think about it. When you have an ideal gas, all these particles, they're bouncing around like crazy in like elastic collisions, but in an real gas, these particles are slightly attracted to one another. They're slightly attracted to one another, so they collide with the sides of the container less, because they're attracted to one another. If they're sticking to one another, they'll collide with the outside walls of the container less. And so that's why we have this A term that's related to the pressure term in the ideal gas law equation. Because if this particle is sticking more to its friends, it's going to collide less with the walls of the container, so therefore will the measured pressure be more or less than anticipated? If it's colliding less, the pressure will be less, and that's what happens. When particles are more attracted to one another, they're going to collide with the sides of the container less. You'll measure a less pressure than indicated, or like than predicted. All right, and that's what the A term corrects for. A term is important at low temperatures, because there's loss of that kinetic energy, because of collisions are inelastic. All right, so hopefully you can see this is how we get the van der Waals equation, where we have this P term with some alterations. We have the V term with some alterations, right? Know when the A versus the B term, what they stand for, when are each of them important. What's not a learning objective for the exam is calculating using this equation. It's just kind of like numbers. It's plug and chug, but there's a lot of places to go wrong. It's not much of a learning objective for this course. So instead, let's do a theoretical calculation that requires no calculations whatsoever, but we're still using the van der Waals equation. Okay, so let's say we have two separate containers, same temperature. Each one contains 1 mole of gas, 1 mole of nitrogen, 1 mole of CO gas. Okay, if they're the same volume, same temperature, shouldn't their pressures, if we used PivNert, right? If we PivNert both these things, what should their pressures be? So if we just did PV equals nRT, if this was the ideal gas law, shouldn't the pressures thus be the same? If it's the same N, the same V, the same T, pressure when it's ideal should be the same. When it's ideal. But what are we talking about right now? Are we talking about ideal gases? No, we're talking about real gases. Okay, so if you just did plug and chug PivNert, you'll get that. So let's now consider them to be real gases. So here are the gases, nitrogen, carbon monoxide. Let's compare the B terms. B stands for what? Size. So what do we want to compare? Their molar masses. And I tell you the molar mass. They're both about, they're not 18. What's nitrogen? These aren't 18. I don't know why I put that. They're 28. I think both of them are about 28. I don't know why I said that. But it doesn't matter. Both of the molar masses are the same. So what do you think their B terms are? Probably the same. Yeah, the B terms are probably the same because molar mass is the same. Okay. So let's compare their A terms now. A stands for what? Attractions, yeah. So let's look at the other piece of information I gave. I gave that nitrogen is a nonpolar molecule, but carbon monoxide is a polar molecule. So just based upon that, which molecule do you think is going to have the larger A term? Which particle sample are the molecules going to be more attracted to one another? Yeah, CO, the molecule that's polar. Yeah, so the A term for CO is going to be larger than N2. All right, the A term for CO. In CO, the particles are more attracted to one another in the carbon monoxide term. Okay, so B terms are the same, but A terms are different. So if we consider both of these gases to be real gases, which one has the higher measured pressure? So we got two balloons, one's N2, one's CO. Which one is going to have the higher pressure? N2 or CO? Which one do we think? Think about how they differ. In CO, the particles are what? They're attracted to one another. So how is that going to affect the pressure? If the particles are attracted to one another, they're going to collide less with the walls of the container. So the pressure in CO is going to be lower. So therefore, which one is going to have the higher pressure? CO or N2? N2, yeah, so N2 is going to have the higher pressure in this case, if we consider them to be real gases, yeah. Adding a, so that's a consequence of volume and pressure, both of those things, because it'll change what that pressure value is. So what we're saying is that the measured pressure is less than the ideal pressure if you add the A component. Just try it for yourself. Just put in numbers. All right. Okay. So that is chapter 10. So that means chapter 10 homework is due on Monday. But I'm going to think about it. So wait until you all read my recaps every week. Yeah. So right now it's maybe due for Monday, but you know, with the end of the semester coming up, we just need to finish it by the end of the year. Maybe I'll push it to after Thanksgiving break. Maybe read my recap email. Okay, so we have 12 minutes. I want to start chapter 11. Yes. Chapter 11, intermolecular forces. Okay, because we only have like 3-ish classes left, so I want to make sure we cover everything. All right, so chapter 11, I already mentioned this, right? What's the A term stand for in the van der Waals equation? Attraction. So now we're actually going to learn what those attractions are and the details for attractions. So for chapter 11, very important, review Lewis structures and polarity and molecular geometry. I want you to know, if I say water, I want you to know what kind of molecule that is in terms of its polarity. Is water polar or nonpolar? Polar, yes. So these are skills that are coming back. This chapter is very, very important for chapter 12 coming up, and it's super important in chemistry 1220. We'll probably review this the first day of class in 1220. Okay, so intermolecular forces are super important because they describe a lot of the properties that we see of our samples. So in chapters like 7, 8, and 9, we talked about chemical bonding, so how we build a molecule, right? How we form chemical bonds to build a molecule. Now we're looking at how do molecules interact with one another. This is intermolecular forces, so like international, it's like between countries. So we're looking at attractions that are between molecules. These are weaker than chemical bonds, but they're strong enough to dictate a lot of properties that we see, okay? All right, so let's think about this. Solids, liquids, and gases. Whether we see a solid, liquid, or a gas at like earthly conditions, like we know water. If I had a cup of water at room temperature, it's a liquid. But oxygen gas at room temperature is what phase? It's a gas, yeah. So all those ideas, like whether we see a liquid, solid, or gas at room temperature, has to do with this balance between kinetic energy of particles. This comes from the temperature of our sample versus the attractive forces between those particles, right? This is what we call intermolecular forces. So the more attracted particles are to one another, do you think it's easy or hard to rip those particles apart to make a gas? Harder, yeah. So samples with really strong intermolecular forces typically have high boiling points. It's harder to make them go into the gas phase because you have to break those intermolecular forces, right? Okay, so let's look at this. Let's think about a solid, liquid, and a gas. Think about the balance between kinetic energy or the temperature of that sample versus the intermolecular forces present. So in a solid, the particles, they're packed together. So who is winning? Kinetic energy or intermolecular forces? Are the attractions of the particles winning, or is the kinetic energy of the particles, are they bouncing around like crazy? Which one is stronger? If the particles are close together, then that means the particles are attracted to one another. So that means intermolecular forces are a lot stronger. So then let's look at gases. In gas particles, how are those particles relative to one another? They're far away. So who's winning? Kinetic energy or intermolecular forces? Kinetic energy, yeah, is winning. In a gas. Then what about a liquid? What do we think? In a liquid, kinetic energy and intermolecular forces are about equal to one another, okay? That the attractions are strong enough to keep the particles in a condensed phase, but not enough to let particles like leave. They can translate around or like, move past one another, but it's not strong enough to leave into become a gas. Okay, so kinetic energy, so temperature versus attractive forces. So we mentioned this idea that we have an A term and a B term from the van der Waals equation. I mentioned that the larger the B term, usually A is larger. Usually. So I just went ahead and graphed all of these points where the y-axis is B, size, and A is attraction. So what we see when I graph these values, we see basically a straight line, pretty close to a straight line. So we see, oh, okay, yeah, as B increases, A increases, right? For most of them, for 90% of them. What about this one? What at? All right, so this idea that water kind of falls away from this line. Water is lighter, but has a fair amount of attractions present. This is what we're going to be talking about, kind of the details of intermolecular forces. There's more than one factor that tells us about intermolecular forces. It's not just mass or molar mass. There's actually more factors. Molar mass is one of them, but it's not the only one. And that's where water falls under. Water has actually more intermolecular forces. It's able to do more than just its mass itself. But in chapter 10, just saying, okay, size, increases, A also increases, was good enough. But we can see that there's actually more factors for intermolecular forces, and it'll explain why water is off of this trend. Okay, so what is an intermolecular force? Okay, do not mix this up with bonding. Bonding, chemical bonding, forms a molecule, forms a compound, right? It's inside a compound. Intermolecular forces are between different molecules. So like, for example, water. Water has an OH bond in it, or two of them, right? That OH bond, that single bond, that's a covalent bond. That's a chemical bond. But water can interact with another water molecule. That's what we're talking about, this weaker attraction between two different particles. So an intermolecular force is just generally an electrostatic attraction. That's what an intermolecular force is. We can have different kinds. We can have an electrostatic attraction between full charges. So something like, lithium plus and chloride minus. A cation is attracted to an anion, but these are full-blown charges. Chloride is a full negative one. Lithium is a full positive one. Those are full charges. But we can also have intermolecular forces between partial charges. You remember these? When did we care about partial charges? In polar molecules, polar bonds, like if in this example, HCl. HCl is a polar molecule. There's a partially negative side and a partial positive side. So these are just partial charges, but there still can be attractions between those substances, partial charges and full-blown charges. Okay, and so the big idea here, and I mentioned it before, is that intermolecular forces occur between different molecules in the same sample, but covalent bonding occurs between bonded atoms in the same molecule. So covalent bonding, that was, chapter 8 and 9. We're done with that. We're done building molecules. Now we want to know, how do the different molecules talk to one another? All right. And so there's 4 different types of intermolecular forces we're going to talk about. And we're going to talk about them in order of increasing strength. So I have here on the side what to look for. Each of these different factors have different trends within them. So the first one, London dispersion forces. All substances have London dispersion, but you want to look at molar mass of the compound. That's usually the thing you look for. All right. London dispersion is most important in nonpolar compounds. Next, we were going to talk about dipole-dipole interactions. All right, so in order to have dipole-dipole, you need to have a molecule with a dipole, meaning you're looking for what kind of molecules? Polar molecules, right? So look for polar molecules or permanent dipole moments. That's what I mean. Next, we're going to look at hydrogen bonding. That one's stronger. There's certain criteria. And then last is ion-dipole interactions, right? So here are the criteria we're going to look at. Yeah. Okay, we got 4 minutes. So let's just talk about this first one, London dispersion. All substances exhibit London dispersion attractions, everything. Okay, anything with electrons can have London dispersion attractions, all right? Even nonpolar molecules, because the idea is nonpolar molecules, well, how are nonpolar molecules attracted to one another? They're just like neutral. There's no charges there. But the idea of what dispersion is are electrons dots on a page? No, they're constantly moving around. So if we have an atom, and it's nonpolar, right, and not charged or anything, those electrons are zipping around the molecule or the atom all the time. So at a certain point, if we let those electrons zip around, at a certain point, maybe 2 of those electrons will just be on one side of the particle or one side of the atom at a time. And so what this does is produce a temporary dipole. So at that moment of time where the electrons are zipping around and they both are on this side of the atom, now we have this partial negative charge over here and a partial positive over here. Just for a moment in time, that's it. And so for that split second, we have this separation of charges. And so now this side is partially positive, so this side might attract electrons off of another atom close by. right? And so this is what we call a temporary dipole. It happens, the more electrons that are present in your substance, the more likely dispersion's is going to happen. So that's why the trend is, as molar mass increases of your substance, as molar mass increases, how do the number of electrons change? It increases. If there's more electrons, there's more chances for dispersion to happen. And so we see that these temporary dipoles are produced, and we can have slight attractions between even nonpolar molecules. All right, so we'll stop there. Come back to this. I'll think about chapter 10. I'll let you know tomorrow. Have a great weekend.